wireless communication systems have rapidly evolved, driven by advancements in 5G technologies like network automation, massive MIMO, and new frequency bands, benefiting various stakeholders from commercial providers to end users. This evolution has enabled applications such as virtual and augmented reality, contactless payments, and enhanced mobile broadband. However, the increasing demand for high-speed, low-latency applications, such as holographic teleportation, and the surge in connectivity requirements due to industrial automation are pushing the limits of 5G. As connectivity density surpasses 106 connections per km2, there is a need to rethink network management strategies, particularly around energy efficiency. This convergence of societal demands and technological capabilities is prompting the development of 6G systems, which aim to create a comprehensive, intelligent, and omnipresent wireless network by integrating space-based communications. Additionally, the limited frequency spectrum necessitates effective management of both intentional and unintentional interference signals, which can vary dynamically over time to ensure reliable signal transmission. In the realm of 6G and beyond, various types of interferences pose challenges to wireless technologies. Wideband multi-interference, in particular, emerges as a significant concern as it increases the likelihood of errors in data transmission, increasing bit error rate, compromising the performance of the wireless system. This interference, if left unaddressed, severely degrades system performance. Existing interference cancellation filters have limitations in effectively removing unwanted signals. This stresses the need for advanced interference mitigation techniques and robust signal processing strategies to ensure reliable and high-performance wireless communication in these advanced networks. Objectives of our project are design an adaptive infinite impulse response digital filter bank using deep reinforcement learning and implement the digital filter bank as a systolic array in an FPGA. This is high-level block diagram of our project. Reinforcement learning is at the core of our project. Briefly explaining, reinforcement learning is a paradigm of machine learning that focuses on how an entity should behave within an unknown environment, so some preferred reward is maximized over time. The typical modeling of an RL problem can be summarized as in the diagram shown here. First, the agent receives an observation from the environment, which we typically call a state, and depending on that state, the agent will take a particular action. Then, as the response for that agent's action, the environment will send him a reward signal, indicating how good of an action he chose, along with the next state the agent ended up in due to that action. And this cycle of state and action continues. And with RL, the agent will learn a better action-taking policy that will maximize the accumulated reward over time. This diagram shows the model we have developed to implement this project's goal of designing adaptive digital filters using RL. Here we have chosen a signal receiver system as the environment. For a certain initial training period, we assume that the signal receiver knows the exact signal it should receive, which we have called here the reference or target signal. Firstly, we take the actual signal the device receives, called the input signal, which represents the reference signal mixed with some interference signal and noise. Then, we slice out a certain number of samples of that input signal and take its magnitude spectrum and feed it as the state for the RL agent. Now, based on this frequency response information, the agent will choose an action, which in this case is same as selecting an ear filter of a predefined order. Then, this filter will be applied to the sliced out input signal partition, and a filter output signal will be generated. Thereafter, to indicate how effective the filter was at extracting out the target signal, an SINR calculation will be performed as per the equation shown in the diagram, and that SINR value will be sent to the RL agent as its reward. Now we will start to present some of our results on RL part. Starting with, here we have the SINR reward vs. No, of training steps curves for learning second-order ear filters over 3 independent runs. Note that this problem has a 5-dimensional action space, meaning that choosing a second-order ear filter is same as choosing a particular combination of 5 real numbers bounded between 0 to 1. You can observe here that all these independent training runs converge to a solution that gives SINR values high as 20 to 30 dB within 1 to 2,000 training steps. Digital filter, either FIR or IIR, can be implemented on an FPGA using Systolic-Array architecture. In this project, we implemented a second-order ear filter and a fourth-order ear filter on FPGA. This diagram represents the second-order ear filter, and each P performs multiplication and accumulation operations. Z1 represents a delay element, but it is a flip-flop in hardware implementation. A system-on-chip SoC from Xilinx typically integrates a variety of components onto a single chip, combining FPGA fabric with one or more central processing unit cores, memory interfaces, I/O peripherals, and other specialized hardware accelerators. ARM core facilitates DMA UART initialization and data transfers. AXI DMA transfers large chunks of data between DDR memory and PL fabric without the intervention of the ARM CPU. UART is a protocol used to transfer data between a computer and FPGA. AXI slave IP transfers IIR filter coefficients from the computer to the PL fabric via UART. This is Vivado implementation of our project and timing report of our design. Both software and hardware need to be run parallel to achieve desired results. Our deep reinforcement learning algorithm needs target and interference signals from hardware, and then algorithm outputs the optimal filter coefficients. Hardware needs to generate modulation signal with interference, and it needs filter coefficients from DRL algorithm to filter the interference signal. These are the results from the hardware implementation of the project. Here includes generated modulated signal and interference signals, also results from filtering bandpass and low-pass signals. Thank you.